today, I will talk about this paper, which 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 treats about the anionic mathematical treats on the anion quantum computing and anionic quantum computing, and this paper just this paper is one of the review paper, so there's no such a new thing on the research field. So I will introduce about the basic notions to study those anionic quantum computing. I'm sick, so my talking might not be well. I'm sorry. Anyway, cut this presentation. So, contents are introduction, preliminaries, TLJ theories, and anionic quantum computations. So, sorry. First, we should talk about the boson, fermion, and anion. In physics, there are any indistinguishable particles, then the wave function gets some phase when we exchange two particles, and boson in boson case in 3D, but in 3D case, boson does not get any phase and fermions get minus phase. But if we ignore, if we delete one dimension, then the loop cannot be shrinked to from outside to inside. So the phase might not become plus minus one. We can get we might get some arbitrary phases when we travel away for the one loop. So we call this some particles that does not act like a boson or fermion as an anion. So, and to treat the anions, we need to consider about the Braid group. For Korean, you can think about there are n strings, and as time goes on, the strings are in great, and you can consider it as a 실타래가 영어로 뭐라고 해야 되나? Yeah, just crazy. And we can take the mathematical notion called group, then you can analyze it as a abstract way. So, and actually this topological quantum computing we need to study some knot theory, and I don't know what the topological quantum field theory, but it relates, and in mathematics representation theory in abstract algebra, in algebraic notion, and more, some to study it. So, yeah, I would introduce about the. I would explain that some representational way to treat anions. So for preliminary, we need to know the group, and a group is just abstract notion which satisfies three axioms. One is associativity, and there exists an identity and inverses. So anything that satisfies those axioms, we call them as a group. Yeah. And the field is there are known definition, but they are we just know about that. We just think that field as a real numbers or complex numbers are sufficient for our case. Just definition. And algebra overall field, we will consider the algebra. The term algebra will appear many times, so I just wrote the definition, but you can think about it as some matrices group, something such as n by n over C. The matrices can be added and multiplied and scalar multiple, right? So there are three operations. So you can just think about the algebra as some mathematical structure with three operations, and their representation is defined in this way, but we can you can think about as representing some group in matrix form. So such as we have plus minus 1 with multiply, then multiply operation, then it can be represented as this matrix and this matrix. It's just an example. Or another example is that exponential I theta, a circle I theta with theta, then we can represent it as some rotational matrix, cosine theta minus. So such thing is called as representation of some group, and that's all of the algebraic preliminaries, and the category notion comes out, but you just take the notation from here, the home C. This is you can think about you can think it as a set of some maps. So I will use this notation after here. And in also the braiding is we can see a braiding as a not when so we need not theoretical notions to treat such as this braid element. Then we will connect this to make some knots to analyze the system, and it makes a knot. So we did this theory, and knot is an embedding of a circle to Euclidean space power, and link is on rotation space. But there are n circles to Euclidean space, such as two rings. Rings are sorry. The links are such as this thing. So two circles are linked. We call in Korean this is called as 연판. Translation. And conflict polynomial is just one kind of knot invariance. We will not use this form, but it's special case after here. So, and last preliminary thing is quantum integer. Just for our easy computation. So just define this this equation. It is called as a quantum integer, and it satisfies this relation. You can easily prove it, and just factorial. We don't need it. Yeah. So for quantum for to treat ions, we first define two variables for later, and we use these diagrams, which called as a here diagram. It is defined with two objects. It's a map from an object to another object, and the objects are n points in unit interval. So we can think this as a 4-to-2 morphism, and they must not they must not cross over, and there might be some loops inside the square. So this is this diagram will use to construct tier algebra, and the two diagrams are called d isotopy if we delete the loops and their topological shape are equivalent. So by using the D isotopy, then we can consider the different diagrams. Maybe 2.22. Then this diagram and this diagram. These two diagrams becomes the basis of 222. So we will treat this as just a basis, basis of the vector space. Just some graphical notation. And the diagrams can be composed. Assume two diagrams D1 and D2, then we can just stack it. Then we get new diagram. So stack and compress. Then we get new diagram D1, D2. So yeah, this composition gives new mapping. So the TL algebra is we call TL and A, and it's just a vector space of the morphisms from n points to n points with the TL diagrams, and we can calculate the its traces by connecting the I points to I points. Then I didn't wrote one thing that if we delete one loop, then we multiply a number d. We defined as a Kaufman variable before, maybe a loop variable. Yeah, loop variable. Just multiply it and eliminate the loop. So the Markov trace is maybe in this case d square. Got it? Yeah. So we can calculate the trace as the number of d to the number of the loops. And the Markov pairing is, you can think as a inner product in vector space, and just so there are two diagrams. Then first invert the first element, first diagram, and stack, and then calculate the trace. Then we can calculate their products like B. Yeah, and it's known that the dimension of the vector space TL and A is nth Catalan number. Cn equals to n plus 1 Cn number, and fortunately we can generate the algebra only with those diagrams. It's trivial and yeah, just define as, and we can get every we can make every element in TLNA by stacking those elements in proper way. So those are just some abstract way to of their relations. Yeah. And actually, the Braid group is written in this way in mathematics, but the sigma you can think the sigmas as the 1, 2, n, and sigma 1 equals to the cross only the first string and the second string, and sigma I makes the I string to the I plus 1 and I plus 1 to I string. Note that the ith string will own the I plus 1 string when they are crossing that. Because this is not equal to the it's okay. Okay. This thing. 줌 비디오라도. 네. So, and the Kaufman bracket is a way to make the Braid group to make another way to construct TL algebra. It's defined as a Stein relation. In Korean, 사례관계. Anyway, this relation can be used as such way. Assume there are sorry. Assume this not, then if increase a function, it's equal to a times a function such that we see this part, then it changes to this plus a inverse f of so this thing, and we define f of trivial not as 1. So this is actually a trivial not if we twist the not. This makes f trivial not equals to a inverse f a of 2 not. So just a way to make a not invariant, but and the invariant function is called the Jones polynomial, and we can make a Jones representation if we send the vector space in some good basis. We can and there are one of the most important notion, which is called the Jones-Wendel projectors. We'll take it as Pn. And it's idempotent and vanish if we compose some UIs. Then we can prove its uniqueness and existence in some process. But I skipped the proof. And by using Chebyshev polynomial delta, then we can construct the general formula of the PNs. As lots of graphics. It's some examples of JWP. And so there are and the last thing we would treat is TLJ categories. And to make the category, we first need the unit trivalent graph. It's the constructed with some first we set some vertices inside the square and on the edges, and then connect them just inside for the inside points we connect them only with 3 edges, and for the edge side for the side points they are only connected with 1 edge. They are called the uni-trivalent graph. Then there can be exist some loops, and we colorize the edges with some numbers. So the numbers, the coloring is admissible if they satisfy these relations. Just the relations was came from the to denote it with the projectors. Just connect just the admissible coloring is sufficient condition and the necessary condition to make the those projector connections valid. And generally it can be 시간이 일단 네. So pause the presentation. In the KakaoTalk, topological quantum computing is different from currently implemented quantum what is the major differences? Actually, I don't know about the research field way, but I think that to implement the topological quantum computing, we need to find anion. So it is believed that there in two-dimension physics quantum liquid, which we can see the fractional quantum Hall effect. That those materials are believed to implement the this anionic quantum computing, but yeah, if you find the anion, then you might get Nobel Prize. So in the research field, yeah, it's it has some distances from the nowadays quantum computing, actually. So is it good for your answer? Your question? Good answer for you? 네, 감사합니다. So, 네? 발표장 화면이 보이더라고요. 발표장이 됐어요? 그러네. 들어가요. So, I will continue the presentation. So, far away we saw about the TL algebra and the unitrivalent graph. And unitrivalent graphs, these are some properties of the JWP, which kills the Chambek terms, and the trace of the projector is equal to this value. Just some calculational result. And the TRJ categories are defined as the collection of the trivalent, unitrivalent graphs. TL algebra. In TL algebra, we just collected the TL diagrams, but here, unitrivalent graph is generalized case of the TL diagram, because if we have no inside vertices, then it is equivalent to univalent graph, which we said as a TL diagram. So the TLJ category contains TL algebra, more generalized thing, and in mathematically, those objects in TLJ category, the objects are just the n finite number of points in H, same with the TL algebra. Thus some n points, but might be colored points, collection of some colored points are objects of the category, and the morphism is denoted with the unitary balance there, and we call it simple object or anyone in mathematical way if it satisfies this condition. Such a thing, such example is just a point with inside a square, colored with 3. Then this diagram would generate the algebra generated with this diagram is congruent with the field, the given field. Just to think the F as a complex set. And the below results are wait. Just wait to calculate the space of the morphism space between two objects. So in here, if we have a different, the first one is when we have different colors, then there is no morphisms between them. So only only when two colors are same, then we get the C. And the second case, A times B and C. So A times B, the tensor product is just a position of 2 points. We can tensor product some diagrams as we juxtapose each diagrams horizontally, and if we can connect them with a unitary graph, and it is admissible, then it becomes C, otherwise 0. Trivial space. And but actually the value of A is in complex number, but in this formula we used the denominator we used Chebyshev polynomial, but the value might be vanished, so we cannot define for specific value of A. But that equals to minus. So the vanishing condition is equal to this. In this, if A to the 4 are equals to 1, then the trace of the projector I minus first projector becomes vanished. Yeah, it's vanished. So if we select the value A as it, then we can only use the R minus second projectors from P0 to PR minus second. So we define the new number K and label set 0 to K. Then we cannot use all the colors but the restricted color set, and it's also mathematical representation to work to use it well. And the b value becomes it. Just so we have to revise the admissive because we cannot use whole integer whole positive or zero integers, but the maximum value is k. So we add new condition here, and there there appears a new rule. We call it fusion rule. Fusion rule not in this way, but let me show you an example of the fusion rule. If we combine 1, 1, then there can be 0 or 2. So then there can be a number 0 or 2. And the fusion rule is noted as 0 times 1 times 1 equals 0 plus 2. Just meaning this thing. And actually the value n abc looks so terrible, but it's actually 0 or 1 and 0 or 1. So we can finally go to the annual quantum computations. So we use the specific value a, and so we call the I don't know why it is named in this way, but this category is related to the topological quantum field theory of Jones-Kaufman theory at level K. In the paper, they explained, but I didn't understand it. But anyway, we can select the value of K. If we select K as 1, then D becomes 1. And K 2, then D becomes square root of 2. And if we select K3, then we get the value of D as the Gordon ratio. So especially we will see that the D equals to K equals to 2 or 3 case. They are named with Ising theory and Fibonacci theory. Thanks. We will denote the representation in level K with n particles with charge I. I don't know why the name of the last index is charge, but they call it charge of the representation. So anyway, to construct the theoretically, the annual computations uses the this tree as a qubit. It is named with fusion trees, and study some charge and and effects. So see some examples. In if the k equals one, then the tree in the unit equivalent graph, we can only coloring each axis with 0 or 1. So there are trivially only one case for each value of I as the factor of n. So the representation row 1 and 0 or 1 is just a this option of notation, but you can understand it as a just a trivial basic, just a trivial representation. So k equals 1 case is not our interest, and for k equals 2, we call it easing theory, and we denote each projector as 1 sigma psi, where 1 is for the vacuum or ground state, and sigma is easing angle, and psi is range with Maillard family. So the calculation can be shown by using the fusion rule before, and the paper the author explained that psi is equal to its antiparticle. They interpreted this equation as the condition of the Majorana fermion. And if we increase the value of n, then there are two cases of trees if n is equal to 2. And if we fix the charge I, then we will especially see the I equals 0 cases. So then the left tree gives just a trivial representation, but in n equals 3 case, then the representation row k equals 2, n equals 3, and the charge equals 1. This representation has two bases, two different trees, and it gives two different directions in the abstract vector space. So this gives 2 by 2 representation, and this goes on as the n increases in easing theory. So they call it this two thing as a binary attribute. I don't know the reason. I couldn't understand the name, but yeah, the circle in the tree is just normalizing the vector basis size. And we goes to Fibonacci theory. Then we only interested in the even number of projectors. So we only use 0 and 2 with with a vacuum of the ground state, and the tau, which named Fibonacci annual. So same way, we can draw some bases, and to so if n equals 1 there, then charge 0 case there are no bases, only charge 2 bases in this, and n equals 2 there are each charge has one basis respectively, and in n equals 3 case there are 2 bases of charge 2 and 1 basis of charge 0, and goes on. Then we can see the relations of this equation, and actually the second term in the right part, it is equal to the n-1 particles of 2 and 0. So it can be we can see that the dimensions satisfies entrance 1 just fn equals to fn-2 plus fn-1. So the theory named from this reason. So in Fibonacci theory, we define 2 qubits in this way, and they are named Fibonacci qubit. So anyway, we are our interest is the quantum computation. So we want to know that the theory can treat the universal case of the quantum computing, and fortunately, if k is not equal to 1 to 4, then the representation can be used to construct universal quantum operators. That's a mathematical result, and yeah, the theorem 411. The notations are anyway, the right side vector space is actually equal to c squared. So the c squared right part is so just think as SU2. And the left side, this part means the representation of this k equals 3 and n equals 3 and I max b1, whatever. The theorem, and theorem, second theorem means 2-qubit system can be universally treated with those annual quantum computation. And the paper finally the paper ends with the result with the John's polynomial approximating the John's polynomial. I said the front part of the presentation. and classically the approximation depends on number p, but in quantum mechanically we can approximate it in complete class, and they didn't prove this approximation, but just they wrote down in the paper the PQP complete result. Yeah. So this is the end of the presentation. So are there any questions? Oh. Not so abstract things. Any questions? What are the advantages of I don't know the advantage of the quantum computing, but in topological way, but the paper introduces the principle of some topological quantum computing way in mathematically. So advantage는 없는 것 같아. 이걸로는.
I have one question. So, as far as I understood, the key point to actually make the topological quantum computer is to find the NIM.
Yeah.
So, and why is it so hard to fabricate and make NIM? NEM. Yeah.
In experimentally.
Yeah. Why is it hard to make NEM?
Maybe I didn't study about the fractional quantum Hall effect, but to implement the those theory in real material, then we have to find the material, but I think that process to find material and implement control the material is hard, one of the hard thing, maybe. So I don't know about the real research field about it.